According to astronomer Andrew Fox, the Milky Way Galaxy can be likened to a hilltop village. He explains that at night, one can observe the torches shining in two nearby villages, namely the Magellanic Clouds and a more distant village, Andromeda. These were the only known villages for a long time until someone combined two lenses to create a telescope and discovered numerous tiny villages scattered throughout the surrounding hills. This discovery led to the realization that the maps needed to be redrawn, resulting in the local group, which is where we reside. Throughout most of human history, it was unfathomable that anything existed beyond the Milky Way. After all, the Milky Way is our home galaxy, and its billions of stars were enough to captivate stargazers for centuries. Even today, with the aid of space-based telescopes and advanced cameras, both amateur and professional astronomers can devote years to studying the Milky Way and its planets, stars, and nebulae. However, peering beyond the Milky Way's delicate halo reveals a fascinating view of the nearby universe and the ongoing evolution of galaxies. The local group is a collection of around 85 gravitationally bound galaxies near the Milky Way, spanning roughly 10 million light-years. This group includes not only the Milky Way and several other bright galaxies visible to the naked eye, but also numerous much smaller galaxies that dominate the local group in terms of numbers. By studying the local group, astronomers can observe galaxies in their entirety and gain a broader understanding of galaxies beyond our own. Astronomers have a unique vantage point on the formation of galaxies in the local group. In this group, small, low-mass galaxies frequently merge with larger galaxies, providing a wealth of information about the evolution of galaxies. The dwarf irregular galaxies, which are devoid of any geometrical structure, are of particular interest to astronomers. Despite their small size, the dwarf irregular galaxies in the local group are worthy of study, as they provide important insights into the larger population of galaxies. According to Marla Gaya, an astronomer at Yale University, studying the extremes of any population helps to better understand the population as a whole. The large and small Magellanic Clouds are the largest and most well-known dwarf irregular galaxies in the local group. They are fuzzy patches visible in the southern hemisphere night sky and lie at distances of 160,000 and 200,000 light-years away, respectively. These galaxies are gravitationally bound to the Milky Way and are thought to contain just a few thousand stars, making them much smaller than the Milky Way. However, each Magellanic Cloud is one of the few galaxies in which individual stars can be resolved, enabling astronomers to study their motion and composition and to build a more accurate picture of how the galaxy formed. Recent Hubble Space Telescope images have revealed that the large Magellanic Cloud is forming stars in dense groups that may be precursors to globular clusters. These groups contain some of the brightest stars in the galaxy, which emit winds that sculpt nearby gas into bubbles and streamers. The study of these intense star formation sites has enabled astronomers to better understand high-mass star formation, a process that is common in galaxies much farther away than the local group. Despite being gravitationally bound to the Milky Way, it is still unclear whether the Magellanic Clouds have completed several Milky Way orbits or if they are plunging into the Milky Way's halo for the first time. The fact remains, however, that the Milky Way's gravity is tearing both galaxies apart. The Milky Way is stripping away gas from the two dwarf galaxies and collecting it in a massive cloud known as the Magellanic Stream. This cloud covers 1/4 of Earth's sky and contains the star-forming material that the Milky Way is collecting, depriving the Magellanic Clouds of their stellar fuel. The observations of the Magellanic Stream provide astronomers with a close-up view of gas cycling between galaxies, demonstrating that larger galaxies can consume their smaller companions. Stars are considered to be factories that produce metals, which refer to elements heavier than helium. Some of these metals become part of nebulae, which later form new stars. As a result, the metallicity of a galaxy, which is the prevalence of metals, generally increases over time, especially for actively forming galaxies. On average, larger galaxies contain a higher fraction of metals than smaller ones, such as the Milky Way and Andromeda. These galaxies contain the highest fractions of metals, which explains why items such as rings, cell phones, and spoons are made of metals. In contrast, dwarf irregular galaxies in the local group have low metallicities and are considered to be chemically pristine. They are composed mainly of hydrogen and helium, similar to the universe shortly after the Big Bang. These galaxies allow astronomers to study what the early universe looked like before stars polluted space with metals. One such chemically pristine galaxy is Segway 2, which was discovered by combing through data collected by the Sloan Extension for Galactic Understanding and Exploration, Segway, survey. Segway 2 orbits the Milky Way, but it is only 1/500th its size, making it a tiny galaxy. Segway 2 is peculiar because it has a low mass and lacks dark matter, a mysterious substance that interacts gravitationally with other matter but does not emit, reflect, or scatter light. Most galaxies contain copious amounts of dark matter, but Segway 2 has relatively little. This suggests that the Milky Way may have stripped off some of Segway 2's dark matter. Despite its small size, Segway 2 has all the properties of a galaxy, albeit with few stars. Astronomers suspect that the local group may contain many more galaxies than the currently known 85, and searches are underway to find more dark matter-dominated galaxies. The Magellanic Clouds, Segway 2, and other dwarf galaxies that orbit the Milky Way are not the only gravitational entourage in the local group. The Andromeda Galaxy, located about 2.5 million light-years away, also has several satellite galaxies. This is not surprising considering that both the Milky Way and Andromeda are the largest galaxies in the local group. According to Benjamin Williams, an astronomer at the University of Washington who studies nearby galaxies, Andromeda is one of the two most massive members of the local group and therefore has a significant impact on the group's evolution. In fact, Andromeda appears to have even more interactions with its satellites than the Milky Way, as evidenced by its more structured stellar halo and lower level of current star formation in its satellite galaxies, both of which suggest a more violent past. Astronomers from the University of Notre Dame and the University of Wisconsin-Madison announced earlier this year that they had discovered a vast halo of gas around M31 using Hubble. The halo, which stretches halfway to the Milky Way and contains metals such as carbon, oxygen, and silicon, may have obtained some of these elements from satellite galaxies that merged with Andromeda. However, the significance of observing large galaxies consuming smaller ones goes beyond a macabre fascination. As Kirby explains, witnessing a dwarf galaxy stretching out until it breaks apart into the smooth outskirts of the Milky Way or Andromeda provides insight into how galaxies grow over time into the ones we observe today, without having to wait for the approximately 5 billion years before the Milky Way and Andromeda collide. Kirby explains that the collision between the Milky Way and Andromeda will result in the destruction of their spiral arms, leaving behind a mostly featureless elliptical galaxy. However, this fate is not shared by the dwarf irregular galaxies in the local group, which will continue to orbit their larger hosts even after the collision, with their stellar populations remaining unchanged. During the collision, the supermassive black holes at the center of each galaxy will orbit around each other, releasing a significant amount of energy. But such black holes are relatively rare in the local group. Only 3 galaxies, including the Milky Way, Andromeda, and a dwarf elliptical satellite of Andromeda called M32, have evidence of a supermassive black hole. Kirby notes that this is not a coincidence, as these 3 galaxies are among the largest systems in the local group. Most of the dwarf irregulars in the group do not have such massive black holes, as they typically have stellar masses of around 100 million solar masses, which is not enough to support a supermassive black hole. The phenomenon of cosmic cannibalism seems to be widespread around large galaxies in the local group, but there are some exceptions. M33, also known as the Pinwheel Galaxy, is the 3rd largest galaxy in the group and orbits Andromeda, yet it shows no signs of central bulges that are typical of merged galaxies. Additionally, its 40 billion stars form a delicate spiral pattern that would have been disrupted by significant gravitational interactions. NGC 604, a massive star-forming region in M33, provides evidence of a significant gas reservoir. If Andromeda stripped away M33's gas in the past, it must have been replenished before NGC 604's first stars formed several million years ago. M33 is an ideal nearby subject for studying disk formation and evolution in a galaxy that experiences minimal satellite harassment, explains Williams. While the other galaxies in the local group exist in relative isolation, the larger Virgo supercluster lies beyond them, containing other distant galaxy clusters. With advanced telescopes and cameras, astronomers can now study galaxies in our home supercluster in intricate detail, but the local group's smaller galaxies remain a significant source of interest.